Welcome back. I'm Muggsy, and today I'm going to explain stoichiometry with limiting reactants. Up to this point, hopefully you've done some stoichiometry problems. And in those problems, there's no talk of limiting or excess reactants. There's just, if I have how much of A, how much B do I make? But in reality, in the real world, that's not quite how things work. Usually we're limited by something in the production of making some products. Here's an example. Let's imagine we're making peanut butter sandwiches. And in order to make those peanut butter sandwiches, we have peanut butter. I don't know, does that look like a peanut? And we have bread. And when we put those together, we make a sandwich, right? Specifically, every peanut butter sandwich, let's say it's 2 slices of bread, so we'll put a 2 coefficient in front, and 2 tablespoons of peanut butter. So we'll put 2 tablespoons of peanut butter as our reactants. And in fact, I won't use 2 jars. I'll just write down a tablespoon. Okay. So now we can actually answer some problems about peanut butter and jelly sandwiches. So let's say I have 1 loaf of bread and I have 1 jar of peanut butter. How many sandwiches can I make? As we established in our formula, and maybe I'll write it down in words instead of pictures, and we're starting with 1 jar of peanut butter and 1 loaf of bread. So we're going to need a little bit more information. And if you look it up, the average loaf of bread has 24 slices. And the average jar of peanut butter has 50 tablespoons. Okay, so how many, I guess I should say, sandwiches can we make from our 1 jar of peanut butter and our 1 loaf of bread? We'll probably have to investigate them both separately. So let's start with our jar of peanut butter. And I guess the first thing we want to know is how many, we know that it's 50 tablespoons, right? So how many sandwiches can we make? So for instance, 1 jar, we want to get rid of jar, and we want to go to tablespoons, TBL. We know that it's 50 tablespoons to the jar, so that means we have 50 tablespoons. Okay, cool. The next thing we want to do, another conversion factor, is we want to get rid of tablespoons and we want to go to sandwiches, right? And we know that for every 2 tablespoons, there's 1 sandwich. It takes 2 tablespoons of peanut butter to make 1 sandwich. Some people like it with more peanut butter, some people like it with less, but let's go with this recipe. Okay, so 25 divided by 2, sorry, 50 divided by 2 gives us 25. Tablespoons cancels with tablespoons, jar cancels with jar, leaving sandwiches. Okay, so there's our answer. We can make 25 sandwiches. Well, not so fast. Let's take a look at our bread next. So we have 1 loaf of bread. And we know that there are 25 slices to every 1 loaf. Okay. So therefore, we have 24 slices. We want to do 1 more conversion. We know that it takes 2 slices to make every 1 sandwich. So we want to get rid of slices. Let's put that on bottom. 2 slices to every 1 sandwich. And so 24 divided by 2 equals 12. Slices cancels with slices, leaving sandwiches. Okay, so the answer is 25 and 12, 2 different numbers? No, we all know this logically. If I have enough peanut butter to make 25 sandwiches, but I only have enough bread for 12 sandwiches, I'm really only making 12 sandwiches. I can only make as many sandwiches as my bread allows. If I want to make more peanut butter and jelly sandwiches, I can keep using the same jar of peanut butter, but I'm going to need to buy more bread. Okay, in chemistry, we call the bread our limiting reactant. Because the bread is what's limiting us. It's what's preventing us from making more sandwiches. Our PB, peanut butter, in chemistry, we would call that the excess reactant. Because we have excess peanut butter. We have enough peanut butter to make 12 sandwiches, and then we still have a bunch of peanut butter left over. Basically enough peanut butter to make another 13 sandwiches, right? 25 minus 12 is 13. So, if I were to ask you this problem, if I have a jar of peanut butter and a loaf of bread, how many sandwiches can I make? The answer would be 12. You can only make as much product as your limiting reactant allows you to. Your excess reactant, it doesn't matter if you have all the peanut butter in the world. If you only have enough bread for 12 sandwiches, you're only gonna make 12 sandwiches, and then you're gonna have some leftover peanut butter, some excess peanut butter. Consider this chemical equation. We have the synthesis of table salt, sodium chloride, from sodium metal and chlorine gas. Up to this point, you've been dealing with questions such as, let's say if we have 5 moles of sodium, how many moles of sodium chloride can we make? And you'll be able to use the mole ratio to answer this problem really easily. You would say for every 2 moles of sodium, there are 2 moles of sodium chloride, so that simplifies to 1:1. For every 1 mole of sodium, there's 1 mole of sodium chloride. And so therefore, 5 times 1 divided by 1 equals, 5 moles. All right. But what this problem is leaving out is, well, what about the chlorine? The chlorine's there as well. How much chlorine do we have? And usually, textbook problems will say something like there's excess chlorine, or don't worry about chlorine, there's plenty of chlorine. Let's say we have a huge chamber of chlorine and just a little chunk of sodium metal. But in the real world, we really do need to work with quantities of both sodium and chlorine, right? And let's say we had 5 moles of sodium and 5 moles of chlorine. Now, how much sodium chloride can we make? Well, we've already established that those 5 moles of sodium go to a 1-to-1 ratio, and so they make 5 moles of salt. But our 5 moles of chlorine have a 1-to-2 ratio. So for every 1 mole of chlorine, we're going to make 2 moles of sodium chloride. So that means we're going to multiply our 5 by 2, and we're going to get 10 moles. Okay, so how much sodium chloride do we make when we have 5 moles of sodium and 5 moles of chlorine? Well, the answer is just 5 moles. And that's because we have enough sodium to make 5 moles of salt, and we have enough chlorine to make 10 moles of salt. But even though we have enough chlorine for 10 moles, we don't have enough sodium to go with that chlorine. That means our sodium is our limiting reactant. It's the reactant that prevents us from making more. Because let's say instead of 5 moles of sodium and 5 moles of chlorine, let's say we had 10 moles of sodium and 5 moles of chlorine. Well, remember, the ratio here is 1-to-1 of sodium to sodium chloride. So if we have 10 moles of sodium, we can make 10 moles of sodium chloride. And if we have 5 moles of chlorine, the ratio here is 1-to-2, we can make 10 moles of sodium chloride. So how many moles of sodium chloride can we make? We can make 10. And in this case, there is no limiting reactant. We're not limited by our sodium, nor are we limited by our chlorine, because they both have exactly enough to make 10 moles. So if we did this reaction, there would be no sodium left over and no chlorine left over. Let's look at one more example. Let's say this time we have 20 moles of sodium. Keep increasing it. Well, 20 moles of sodium would make 20 moles of sodium chloride because that ratio is still 1 to 1. And our ratio of chlorine to sodium chloride is still 1 to 2, so 5 moles of chlorine is still going to make 10 moles of sodium chloride. So now, how much sodium chloride can we make? We've got enough sodium for 20 moles, we've got enough chlorine for 10 moles, so we can only make 10 moles. We're limited by our chlorine now. Previously we were limited by our sodium. Now we're limited by our chlorine. We call that our limiting reactant. And so if you did this reaction, if you took 20 moles of sodium metal and you reacted it with 5 moles of chlorine gas, at the end of the reaction, there would be no sodium left and there'd be no chlorine gas left because we used it all up. It's our limiting reactant. And there would be about 10 moles of sodium left unreacted in its pure metallic form. We'd also have 10 moles of sodium chloride that we created. Our sodium, the reactant that's not the limiting reactant that you have extra of, we call that the excess reactant. Because there's extra of it. There's some excess left over. Okay. So now with our stoichiometry problems, we actually have to consider how much of the stuff we can actually make looking at all the relevant reactants and not just one of the reactants. The exception would be if I told you I had 10 grams of sodium and all the chlorine in the world, or excess chlorine, or don't worry about chlorine, we got plenty of chlorine. Unless the problem says something like that. If it says something like we have 10 grams of sodium and 10 grams of chlorine, then you actually need to do the problem. So let's do that now. Let's say we have 10 grams of sodium and 10 grams of chlorine. How many grams of sodium chloride can we make? Okay, well, the first thing we need to do is figure out if we have 10 grams of each of these, how many moles is that, right? So for our sodium chloride, if we have 10 grams of sodium, we've got our conversion factor here. We want to get rid of grams, we want to go 2 moles. In order to get moles, we have to use the molar mass. And so since sodium is just one element, sodium, the molar mass is the same as the atomic mass. You can just look it up in the periodic table. It's 23. To every 1 gram, right? No, I screwed up my conversion factor. It's not 23 moles to every 1 gram. 1 mole of sodium has a mass of 20 grams, 23 grams. Man, messing up a lot. Okay. In order to do the same for chlorine, we would basically take our 10 grams of chlorine and we'd multiply it by the same conversion factor where we want to get moles, we want to get rid of grams, and we have to use the molar mass to do so. Now chlorine's a little bit different. If we look up the molar mass for chlorine, it's 35.5. But of course, every 1 chlorine molecule, instead of being an individual atom like with sodium is 2 chlorines stuck together. So we got to multiply that by 2, and we get, what, 71 grams to every 1 mole. Okay, so if we do the math for each of these, if we put these into our calculator, we'll see exactly how many moles they both create. Okay. 10 divided by 23 gives us 0.435 moles of sodium. And 10 divided by 71 just gives us 0.141 moles of chlorine. Okay. We still don't know which of these two is our limiting reactant though, and how much sodium chloride we're gonna make. So in order for that, we're gonna actually have to go from moles of sodium and moles of chlorine to moles of sodium chloride. So let's do that. So if we have 0.435 moles of sodium, we want to get rid of moles of sodium. And same thing here, we want to get rid of moles of chlorine. And what we want to get is moles of sodium chloride. And to do that, we use the mole ratio. So let's look it up. For every 2 moles of sodium, there's 2 moles of sodium chloride. That simplifies to 1 to 1. So that just equals 0.435. Cancel, cancel, moles of sodium chloride. Up here, the ratio is actually there's 2 salts for every 1 chlorine. So that's a 2 to 1 ratio. So we do 0.141 times 2, which is like 0.282 moles of chlorine. Okay. So now we have our moles, I'm sorry, not moles of chlorine. So that makes 0.282 moles of sodium chloride, salt. Okay, so we have enough sodium to make 0.4 grams of sodium chloride, and we have enough chlorine to make 0.3 almost grams, moles of sodium chloride. So we have more sodium than chlorine, right? Even though we have 10 grams of each, our sodium creates more sodium chloride than our chlorine does. Now, a lot of students at this point want to keep going and go from moles to grams. You don't need to do that for both of these, right? You only need to do it for your limiting reactant, because you can only make as much sodium chloride as your limiting reactant allows you to. And our limiting reactant in this case is our chlorine. Whereas our sodium is excess. Now, why is that when we have 10 grams of sodium and 10 grams of chlorine? Well, it really comes down to their molar masses, because the molar mass of sodium, as we established earlier, is 23, and the molar mass of chlorine is 35.5. So chlorine has a bigger molar mass. So what that means is 10 grams is more moles of sodium than it is of chlorine, because every individual mole of sodium weighs less, so you can have more of them, right? 1 mole of sodium is 23 grams, but a mole of chlorine is bigger, 35 grams. So these 10 grams don't give you the same number of moles. You get more moles of sodium than you do out of chlorine. We've determined that sodium is our excess reactant and chlorine is our limiting reactant. And we know that we have enough sodium to make 0.435 moles of sodium chloride, and we know we have enough chlorine to make 0.282 moles of sodium chloride. So how much can we make? We can make 0.282 moles, right? We can only make as much as our limiting reactant allows us to. If I have enough peanut butter for 1,000 peanut butter and jelly sandwiches, but I only have enough bread for 1, how many peanut butter and jelly sandwiches can I make? I can make 1, right? Because I'm limited by bread. In this case, I'm limited by chlorine, so I can only make as much NaCl as my chlorine will allow me to. So I would suggest taking the number that you got for your excess reactant and just ignore that. Erase it. Well, don't actually erase it, leave it in your work, but you're not going to do anything else with it. A lot of students want to convert that to grams, but you don't need to do that. Whichever one makes the fewest moles is going to be your limiting reactant, and that's the only one that you need to convert to grams. So let's take our 0.282 moles of sodium chloride, and let's convert that one to grams. So we want to get rid of moles of sodium chloride. We want to go 2 grams of sodium chloride. For that, we're going to need the molar mass. Sodium is 23, chlorine is 35.5. So that's going to give us a total of 58.5, right? So 58.5 grams to every 1 mole. Okay, so if I have 0.282 moles times 58.5, I get 16.5 grams, because moles cancels with moles, leaving grams of sodium chloride. Okay, so again, here's where it kind of makes sense. If I had 10 grams of A and I add it to 10 grams of B, how much of the mixture would I have, AB? You would expect it would be 20 grams. And if they went together perfectly, that would be true. The problem here is that's not a perfect ratio, right? So I'm gonna expect my actual answer to be a little bit less than 20 grams, right? But probably more than 10 grams, right? Because each of these are 10 grams, so it should at least be as much as one of those. And in reality, that's what my answer is. I make 16.5 grams of sodium chloride. Now, what if I asked you, okay, so chlorines are limiting reactant, right? And sodium is our excess reactant. Now remember, we live in a universe in which the first law of thermodynamics exists, so matter and energy can neither be created nor destroyed. So how much total stuff did I have in my reactants? I had 20 grams. So when the reaction is done, there should be in our products 20 grams of stuff. But as you can see, there isn't. There's 16.5. And that's because some of this 20 grams is our leftover excess reactant, in this case, pure sodium metal. So going into the reaction, we have 10 grams of sodium metal and 10 grams of chlorine gas. Coming out of the reaction, we should have 16.5 grams of sodium chloride, table salt, and plus 3.5 grams of sodium metal, unreacted leftover sodium metal, because it's our excess reactant. We have excess of it, right? Because now 16.5 plus 3.5 equals 20 grams. So if you need to calculate how much of the excess reactant is left over, you can do that pretty easily by just taking the sum of all the reactants, that's 20 grams of mass, and comparing that to the sum of how much of your final product you create. And we created 16.5. So 16.5 and 20, 20 minus 16.5 just means that there were 3.5 grams of sodium left over unreacted. Again, if our sodium and chlorine were kind of perfectly calculated so that there was no excess reactant and no limiting reactant, we would use, some amount, let's say 20 grams total of sodium and chloride, and it would make 20 grams of sodium chloride. But because we didn't, because we have an excess reactant and a limiting reactant, we make some amount, 16.5 grams of sodium chloride, but we also have some amount of our excess reactant, sodium, left over, 3.5 grams. Let's look at some other examples. Let's look at the synthesis of water from hydrogen gas and oxygen gas. If you burn hydrogen gas in the presence of oxygen, you create water in the form of steam. Okay, hopefully you've noticed by now that this equation isn't balanced. We have two hydrogens, that's great, but we have 2 oxygens in our reactants and only 1 oxygen in our products, so we're gonna need a 2 coefficient here, which means we now have 4 hydrogens in our product, so we're gonna need a 2 there, which gives us 4 hydrogens in our reactants. Okay, so what if I had, let's use 10 grams again, 10 grams of hydrogen gas and 10 grams of oxygen in a little chamber, and I'm going to burn them together. How much water will I make? Well, you might look at 10 plus 10 and assume that the answer is going to be 20 grams, right? And that kind of makes sense, right? Because we live in a world in which the first law of thermodynamics tells us that the reactants must be equal to the products. So if the mass of the reactants is 20 grams, then the mass of the products must also be 20 grams. But that doesn't mean that we're necessarily going to make 20 grams of water, because again, we might have a limiting reactant here. We might be limited by our hydrogen, or we might be limited by our oxygen. The only way to find out is to go ahead and crunch some numbers. So let's do it. Let's go from hydrogen to water, and let's go from oxygen to water, starting with our 10 grams. Okay. So if we have 10 grams of hydrogen, we want to get rid of hydrogen, and we want to go to, grams of hydrogen, we want to go to moles of hydrogen. If you look in the periodic table, hydrogen is the smallest element there is with a mass of 1.01. So H2 would just be 2.02 grams per mole. Okay, so that's going to give us roughly, I'm not going to blow my calculator here, 5 grams cancels with grams, moles of oxygen. And then if we want to figure out, I'm sorry, did I say moles of oxygen? Moles of hydrogen. Let's just do that again. Okay, so if I have 10 grams of hydrogen, I divide that by its molar mass, 2.02, and I get roughly 5 grams, or 5 grams cancels moles of hydrogen gas. Now, if I want to know how much water that's going to make, I'll have to use the mole ratio, and you can see there's a 2 here and a 2 here. So for every 1 mole of hydrogen, I'm going to make 1 mole of water, right? Because 2 to 2 simplifies to 1 to 1. Moles cancels with moles, and I'm going to have 5 times 1, 5 moles of water. Okay, so my hydrogen, 10 grams of hydrogen, gives me enough hydrogen to make 5 moles of water. Now you might be looking at this problem and say, well, we want to know how many grams of water are going to be produced. I get that, but you don't need to go that far, right? Because we're really just going to stop at moles until we know which one of these two, hydrogen or oxygen, is our limiting reactant and which one is our excess reactant. So let's hold off on that step for now and let's look at our oxygen. So we just calculated that with 10 grams of water, we can make 5 moles of H2O. And I told you to stop there because we're now going to look at our oxygen, and let's do that now. So again, we have 10 grams, and we're going to figure out for those 10 grams of O2, how many moles of O2 that is. And we know that for every 1 mole of oxygen, there are 32 grams. That's because the molar mass of oxygen is 16. 16 times 2 is 32. So now we're actually going to get a much smaller number than we did for our hydrogen because we have a much bigger molar mass, right? The molar mass of H2 is 2, but the molar mass of O2 is 32. That's 16 times bigger. So that means 10 grams is going to make a lot fewer moles. Specifically, it's going to be like 0.3, something like that, right? 10 divided by 32. 0.313. Grams of O2 cancel with grams of O2, moles of O2. Now we're not actually done because we want to figure out how much water we're going to make, not O2. So we got to get rid of moles of O2. We want to go to moles of H2O. And we know that for every 2 waters, we're going to require 1 O2. So that's a 2 to 1 ratio. So we're basically just going to multiply this number by 2 to get 0.625 moles of water. Okay, hopefully you've noticed that that's a much smaller number than 5 moles of H2O that we can make with our hydrogen. And so that should tell us right there what the limiting reactant is and what the excess reactant is. We have enough oxygen to only make 0.62 moles, but we have enough hydrogen to make 5 moles, much more. That means our hydrogen is our excess reactant, and our O2 is clearly our limiting reactant. And so how much H2O can we make in moles? We can make 0.625 moles, because we can only make as much as our limiting reactant allows us to. So if we react 10 grams of hydrogen, 10 grams of oxygen, we're going to use up all 10 grams of that oxygen, and we're going to have a bunch of leftover hydrogen. So let's actually answer this question. Originally I asked you, what mass of H2O can I create? And all I've given you so far is my moles of H2O. Now I told you not to earlier calculate how many grams of H2O this would be, because you don't need to do it twice. We don't need to calculate how many grams of H2O would come from that 5 moles, because that's our excess reactant. We only need to do that calculation for our limiting reactant. So it's basically just to save you time and energy. But let's do it now. Now that we know the number of moles of H2O, let's figure out how many grams of H2O that is. And we do that using the molar mass. Hydrogen's 1, and we've got 2 of them, so that's 2. And the molar mass of oxygen is 16. 2 plus 16 is 18 grams per every 1 mole of H2O. Okay, moles cancel with moles, and then we have to do a little math here. 0.625 times 18 equals 11.3 grams of H2O. Perfect. This is a really good answer. The reason I like this is if we had a perfectly balanced, if this reaction was perfectly balanced and there was no limiting or excess reactant, we would have 10 grams and 10 grams of reactants, and we would have 20 grams of our product, H2O. But that's not the case, right? One of these we have way more, our hydrogen, and one of them we have way less, oxygen. Now, even though I said more and less, it's the same amount, right? But 10 grams is a lot of hydrogen, because hydrogen is very small, and it's very little oxygen, because oxygen is much bigger. So our final answer is going to be somewhere between 10 grams and 20 grams. And in fact, that's what we got, 13 grams. So that's a good guide. What if I asked you how much leftover hydrogen would there be when we're done with this reaction? Well, that's actually a really simple problem to solve. And again, that comes back to our first law of thermodynamics. If we have 20 grams of reactants total, 10 plus 10 is 20, we need to have 20 grams of product. So thinking that we're going to have 20 grams of stuff at the end of this reaction isn't incorrect. That is correct. It just doesn't mean that it's going to be 20 grams of water. In fact, we only produced 11.3 grams of water. But if we're supposed to produce 20 grams of stuff, and we only produced 11.3 grams of stuff, we can just take our 20 grams, subtract 11.3 grams, and we can get something like 8.7 grams, is that right? I hope so, of leftover H2. Because, again, if we have 20 grams of total reactant, we need to have 20 grams of product. And we know that H2 is our excess reactant. So some of it bonded together with the oxygen to make water, but there was a bunch of it that was just totally unbonded and left over. How much exactly? 8.7 grams, which we can get just by taking the total mass of our reactants and subtract the mass of the product that we made, H2O, to tell you how much leftover reactant there must be. Now, leftover reactants, surely that might also include O2. Well, no, it won't include oxygen, because oxygen's the limiting reactant, so we used it all up. Just like if I'm making peanut butter sandwiches and I'm limited by bread, how much bread is left over? None. There's no bread left over because it's my limiting reactant. What is left over is a bunch of peanut butter, and we can calculate that like we just did. We take our total expected mass, we subtract away the mass of what we actually got, and that'll tell us the mass of leftover excess reactant. Okay, let's look at one last example. Let's say we have the neutralization of calcium hydroxide with hydrochloric acid to produce calcium chloride and water. First thing we should do is, of course, check to see if the equation's balanced, which it isn't. We have one calcium here, one calcium there. We have one hydrogen here, three hydrogens, I guess. Here we only have two. Here we have two oxygens. Here we only have one. Okay, so let's put a 2 in front of that H2O. Now we have 2 oxygens in the reactants, 2 in the products. Those are good. We don't have enough hydrogens though, so let's put a 2 in front of this. And now we have 4 hydrogens, 2 chlorines, 2 chlorines. We're all balanced. Okay. So let's do a similar example to earlier. Let's just keep going with our 10 grams. Let's say we have 10 grams of calcium hydroxide and 10 grams of hydrochloric acid. I'll use different colors for these. How much calcium chloride will I make? Okay, so let's go through and do this problem now. So the first thing we're going to want to know for each of these is if we have 10 grams of calcium hydroxide, how many moles is that? So we want to get rid of grams and go to moles. And same thing for our hydrochloric acid. If we have 10 grams of HCl, how many moles is that? And in order to do both of those, we'll need the molar masses. So let's do some molar mass calculations. Calcium, if you look it up in the periodic table, has a molar mass of 40.1. Oxygen is 16, and there's 2 of them, so that's 32. And hydrogen is 1, and there's 2 of them, so that's 2. Okay, so that gives us 74.1 grams per mole. Let's do the same thing for our hydrochloric acid. Chlorine is 35.5 grams per mole. Hydrogen is 1, so that's 36.5 grams per mole. Okay, so right away you should be able to look at these and see that calcium hydroxide has a bigger molar mass, almost twice as big, and so it's going to have fewer moles than HCl. Even though it's the same mass, 10 grams and 10 grams, because it has a bigger molar mass, 10 grams is going to make a smaller number of moles than 10 grams will for hydrochloric acid. Let's get those actual numbers by using our calculator. So 10 divided by 74.1 is 0.135. Oh, did that wrong. 0.135. moles of calcium hydroxide. And for our HCl, 10 divided by 36.5 gives us 0.274 moles of hydrochloric acid. Okay, so right away, it's a smaller number for our calcium hydroxide and a larger number for our HCl. Okay, does that mean our calcium hydroxide is our limiting reactant? Well, not quite, because we still have to take their mole ratios into effect, right? And so if we want to actually figure out how much calcium chloride we're going to make, the mole ratio for our calcium hydroxide is for every 1 mole of calcium hydroxide, we're going to make 1 mole of calcium chloride. And so that's going to give us the exact same number, 0.135 moles of calcium chloride. With our hydrochloric acid, it's a little bit different in that for every 2 moles of HCl, we're going to make 1 mole of calcium chloride. So therefore we need to divide this number by 2 and get 0.137. Oof, close. 0.137 moles of calcium chloride. So it turned out our calcium hydroxide is in fact our limiting reactant, but not by much. When we take the mole ratio into account, they get really, really close. But it is going to be our calcium chloride. So if our calcium hydroxide. So that's our limiting reactant. Therefore, our HCl is our excess reactant. Okay, so when we're calculating how much calcium chloride we're going to make, we don't need to think about our HCl at all. We just need to think about our calcium hydroxide. And we know already that we're going to make 0.135 moles of that calcium chloride with our calcium hydroxide. So it's going to be easy to convert that into grams. So far in this problem, we've determined that our calcium hydroxide is our limiting reactant, and we only have enough calcium hydroxide to make 0.135 moles of calcium chloride, but we want to know exactly how many grams that is. So let's convert from moles to grams. Moles calcium chloride on bottom, grams of calcium chloride on top. Calcium has a molar mass of 40.1 grams per mole. Chlorine, 35.5, and there's 2 of them. So I guess I'll write it down twice there. Whoa. Is it 111.1? That's kind of a crazy number. Well, I guess we can just round that to 111, 3 sig figs. Okay, so for every 1 mole of calcium chloride, there are 111 grams. It's a really big compound. And so 0.135 moles times 111 is roughly 15 grams. I guess we'll do that in blue to be in keeping with the pattern we've got up above. 15 grams. And now we don't have a question mark anymore. We can just put in 15 grams. Okay. So we're in kind of a slightly more difficult situation than last time. Oh, I guess I can just make it up there. Because previously we only had one product. We were taking sodium and chlorine and making sodium chloride, or hydrogen and oxygen and making water. In this case, we actually have 2 products, calcium chloride and H2O. So we can't just say, if we wanted to know how much HCl is left over, we can't just say 5, because we have 20 grams of total reactants. So we should have 20 grams of total products. Because we're also going to make water, and that's going to add to the mass of our final equation, right? So in order to do this, we need to basically go back to our limiting reactant, calcium hydroxide. So let me just go over what we've done so far. We've determined that calcium hydroxide is our limiting reactant, and that starting with 10 grams of calcium hydroxide, we can make 15 grams of calcium chloride. We don't know how much water we can make yet though, and we don't know how much HCl is left over at the end of the reaction. So let's figure those out now. So we said we have 0.135 moles of calcium chloride. That's also how many moles of calcium hydroxide we have. Because the mole ratio here is 1 to 1. So how many moles of water do we have then? Well, the ratio here is 1 to 2. So we just need to use that 1 to 2 ratio. For every 2 moles of water, we only need 1 mole of calcium hydroxide. Okay, so we just take our 0.135 and we multiply it by 2 to get our moles of water, which is going to be 0.27 moles of H2O. Okay, and we actually want to know how many grams of water that's going to be, right? So we're going to need to take our 0.27 moles of H2O and multiply it by the molar mass. Moles of H2O, grams. And hydrogen's 1, and there's 2 of them, so that's 2. Oxygen has a molar mass of 16, so 16 plus 2 gives us 18 grams per mole for water. That's one that a lot of students memorize. Okay, so we have 0.27 moles times 18, and that gives us 4.86 grams of water. So with our limiting reactant, we have enough calcium hydroxide to make 4.86 grams of water. Interesting, because you'll notice we're very, very close. Remember, when we looked at our limiting reactant and our excess reactant, there wasn't a huge difference. Even though calcium hydroxide is about twice as big as hydrochloric acid, there's 2 hydrochloric acids required for every 1 calcium hydroxide. So they almost worked out to be equal. In fact, it's very, very close because here we have 20 grams of total reactant, and here we have 19.86 grams of total product. And so that's a very small difference. So when this reaction goes, we're going to use up all of our calcium hydroxide because it's our limiting reactant. We are going to have some HCl left over, however. How much? Almost nothing. 20 minus 19.86 is going to be 0.14 grams excess hydrochloric acid. So this is actually a very close reaction. You can see these limiting reactant problems. They're really not any harder than the stoichiometry you've been doing, but you do need to use some logical thinking, and that can be kind of a struggle. But just stick with them, practice them, and then always remember the laws of thermodynamics. If we have 20 grams of stuff that we're starting with, then we need to have 20 grams of stuff that we ended up with. We can't just make matter disappear. I wish you the best on these problems. I'll see you next time.